Hey guys, welcome back. Well, I've decided to make a little course correction and set up my SCT with a one-shot color camera, a filter drawer, and just a couple of filters for use in imaging during galaxy season with this scope. What kind of a huge mistake did I just make? Let's find out. So why did I go this route? Well, first of all, I wanted to try to improve some consistency with my imaging systems by having a one dedicated imaging train, at least for the SCT. I'll take that repaired Ultimate Power Box and plant it on the SCT, and I figured I'd go ahead and buy this one-shot color camera, the 294MC, and put it on the SCT, and probably won't use that camera with any other of my refractors. They'll all be monochrome based systems, primarily for shooting nebula and maybe a galaxy cluster targets here and there. I was going to use the 294 on the SCT, but I wasn't going to use it in bin 1 mode. And so since I wasn't going to do that, I decided to go ahead and just get the 294 since it always operates in what is effectively bin 2 mode in terms of the 294 And I think the pixel scale will be fine, certainly for the full focal length of the SCT without the focal reducer. It gets a little bit dicey with the focal reducer installed, but by and large, I should be getting some decent images out of it. Plus, having a one-shot color camera pairs well with the kind of targets that I'll be shooting with the SCT. And I got to tell you, I haven't been all that happy with the galaxy images I've been getting out of my L, R, G, and B filters, although I don't think it's the filter's fault. I'm pretty sure it's my problem, but for some reason I just felt like I was getting better images or at least better color out of my one-shot color camera, the DSLR that I started astrophotography with. Plus, I'll be using some filters that will help block out some light pollution and sensitivity to moon glow, and hopefully that will expand the number of imaging nights that I have at my disposal when I'm using this imaging system. Now, I do have some concerns. I just finally resolved the focusing issue with Nina and my ASI 1600 last Galaxy season. So now I'm going to restart that learning process with this particular camera, but I'll be using filtered light, which is a bit of a daunting task. That's one of the hurdles that I have, one of the concerns I have, and also making sure I can do plate solving with the filtered light as well. So there'll be a learning curve or 10 to go along with this course correction. But it does give us an opportunity to go back and talk about that good old fun topic, back focus. I'll tell you, this back focus thing with the SCT is a pain, primarily because Celestron does such a lousy job documenting what the back focus ought to be and where it ought to be measured from. So I thought I'd go ahead, since I'm reconsidering this imaging train, and we would talk about this once again. Now, I've got the SCT, the non-edge SCT, and those back focus distances are different from the edge SCT. So if you're using an edge, don't pay any attention to these numbers. I do have the C9.25, and based on this table that I got from Celestron support, I don't believe there's a table like this at all in the SCT documentation. And the SCT was my first telescope, so back focus wasn't in my vocabulary at the time. But I have since found this table, and it tells me that I need 139 millimeters measured from the primary mirror baffle tube lock ring. That sounds very specific, but it's a little more ambiguous than you might think. We'll take a look at that. I'm also using an off-axis guider with this system, and one of the things I always found curious is that the adapter, this is the part that plugs into or screws onto the back of the SCT or the back of the focal reducer, they list as having an optical length of 25.3 millimeters. But if you take out a pair of calipers, you're measuring 33.3 millimeters. And this is actually a hint that the tricky thing Celestron is doing here. What they've done is to subtract the thread length that goes into the SCT adapter from the actual length. And what they're essentially telling you is you got to measure from the back end of the threads. So what I'm going to be doing is coming up with an arrangement of spacers and equipment that give me 139 millimeters for the native focal length and use 105 millimeters with the focal reducer. Now here's that primary mirror baffle tube lock ring. Problem is, Celestron says you need to measure from here. Well, that's great, except most manufacturers, you would be measuring from this surface and you would exclude the threads from the measurement. But what Celestron wants you to do is actually measure the back focus from here, the back of the threads. Now, I did some experiments, unintentionally, mind you, on the effect of changing back focus and what that effect is on the focal length, and this is what I've gotten over the years. When I first bought this scope, it was my first scope. I also bought the T adapter and the T ring for my Canon DSLR. And you'll notice that there's a flange here that will bear up against the threads. This ring here is loose and it is threaded, and when you thread that on, it clamps this surface here against whatever it's mating against. But in this way, the distance from this flange back to the DSLR sensor is 105 millimeters. And what Celestron is assuming and intending is that you'll pair this piece here along with their focal reducer for this scope, and then that's where the 105 millimeters comes from for the back focus with the focal reducer. Now, nowhere does it say don't do this or this isn't the case when you're not using the focal reducer, but that didn't stop me. I didn't have that information. And so when I first was using this scope, I would take my DSLR with this T adapter and just plop it onto the end of my SCT and tighten down the ring here. And so in effect, I was using the SCT at native focal length, but with a back focus of 105 millimeters. And when I go back to look at those images, at 105 millimeters of back focus, the plate solution tells me that the focal length of those images is around 2,220 millimeters. Nowhere near the 2,350 millimeters that is the theoretical focal length for this particular scope. And then in a subsequent year, I was setting the system up and I ended up leaving out an adapter, so this is a mistake, but it took me down to a back focus of just over 90 millimeters, and it also reduced my focal lengths to 2,180 millimeters. And then finally, I found that table we were just looking at, but I didn't know where to measure from. So I was assuming we were measuring from back here, and that gave me a focal length of 2,280. And now lately, in the past couple of years, it's sunk in that no, Celestron wants you to measure the back focus from the back of the threads, not at the back of this outer ring here. And then when you do that, you're back at 139 millimeters, and I'm getting 2,310 millimeters for a focal length, which is about 98% of the advertised focal length. So here are the pieces I'm going to put together to achieve the imaging train with the focal reducer and without the focal reducer. With the focal reducer, I will go straight into the off-axis guider. Then I can screw on the ZWO filter drawer. This is the 21 millimeter thick filter drawer with an M48 internal thread that pairs up with the external M48 thread on the off-axis guider. That leaves me with an external M42 thread that I can then go into that 11 millimeter spacer that comes with the ASI294MC. And of course, with this spacer, it's got a internal thread on the other side as well, which pairs up with the external M42 thread on the camera. And I may or may not need some spacers or shims to go in between here to round out the difference. Now, in the case of the optical train without the focal reducer, I'll probably start off with a 1-inch spacer that I got from Blue Fireball and Vegeta Astro. It has SCT threads. It's an inch long, but of course we have to subtract off the thread length at the back end of the SCT. Then the SCT adapter of the off-axis guider will screw onto it. I can then go into the ZWO filter drawer. However, the Celestron off-axis guider is pretty good in that it comes with a number of adapters and spacers to use. And so what I can do here is, instead of using the M42 11.55 millimeter adapter on the other side of the filter drawer, I can use the M48 version of this adapter that comes with the off-axis guider and put it between the off-axis guider and the filter drawer, so that way I can keep the filter drawer as close to the camera as possible. And then I'll just have that 11 millimeter spacer with ZWO, maybe a spacer to go into to round out the spacing, and then that will connect me back to the camera. I worked up a little Excel table here with the optical links of the various pieces that I'm considering, and then I go through and just type in a 1. If I type in a 1, it copies that number over, and then I add all these up, and sure enough, I get 139.6 millimeters. Now, one of the things you might want to do, I took several of these pieces here, assembled them as a separate unit before I put them on the SCT, and measured the length using the calipers, and found out that the numbers I'm using in this table somehow are providing me with 0.5 millimeters more than I actually get when I measure it. And so that's why I'm going over by about half a millimeter, so that wherever that 0.5 millimeter error is in this table, it will be corrected, and I'll be back to pretty close 139 millimeters as measured from the back end of those threads on the SCT. With the focal reducer, I've got basically the same thing coming directly out of the focal reducer into the off-axis guider, and then I get 105.4. Again, that extra 0.5 millimeters is somewhere buried in these numbers. So this will bring me back to 105 millimeters for this particular scope. And when I look at the pixel scale for the two cases here, 2 times the pixel scale gives me the Nyquist limit. And as long as my Nyquist limit is below the actual achieved full width at half maximum that I'm getting out of this scope, which is a little over 2 arc seconds, then the pixel scale is fine and I will be oversampled ever so slightly and won't be wasting resolution because the pixels are too large. So this will work out great with no reducer. It's acceptable with a reducer and a one-shot color camera. So I've decided just to go with my first trial configuration and use the focal reducer and see what happens. One of the primary reasons for using the focal reducer is it reduces the challenge of finding guide stars for the OAG. It provides more light, smaller stars for focusing and for plate solving. And so hopefully the focal reducer will reduce some of those concerns that I have. Based on images I took with the focal reducer and that key adapter and DSLR, I was getting a focal length of 1320, which is much lower than what I should be getting if that focal reducer is in fact a 0.63 focal reducer. In other words, it's supposed to convert an f10 system to an f6.3, and therefore I should be able to multiply 0.63 times the 2350 millimeters at native focal length, and that gives me the 1480. So it's very odd that I'm getting such a different number. I asked Celestron about this some time back, and they said, well, the focal reducer was out long before the C9.25 was, so it may not be operating at 0.63 with that particular telescope. Well, that's part of the testing process when you put an optical train together and find out how it really works. Another thing that's going to happen is because I've been changing the setup of pieces that go between the off-axis guider and the camera, I'm going to need to verify that the distance from the imaging sensor and my ASI-174 down to the center of the mirror here is equal to about 65.3. I'll have to achieve that in order to have focus with the off-axis guider and simultaneous focus with the imaging system. So that's one of the things that I'll have to be testing early on. Now here's what the final arrangement looks like with the focal reducer. I've got the focal reducer here. There's about once you screw on this SCT adapter, the height from this ledge on the focal reducer to the end of the threads is about 10 millimeters. But this is about a 2 millimeter gap when you put on the SCT adapter and it uses up all the threads. So that's why it appears that Celestron is subtracting 8 millimeters of thread length off the actual physical length of this part so that you'll be measuring from the end of the threads for your back focus. Then we go into the body of the off-axis guider itself. Then I've got the filter drawer and the 11 millimeter adapter and a 0.5 millimeter shim, and that should get me pretty close to the 105. All right, let's take a look at a cross-section through the off-axis guider. One of the things you have to think about is which way do you want the imaging sensor of the off-axis guider to be oriented. I connected to the guide camera using Sharp Cap and recorded a video as I stood and rotated this camera around on its axis. So let me show you what that looks like. Okay, so we're in Sharp Cap and you can see I'm rotating the camera a bit now. And as we get up to this edge where the bright spot is along the long edge, that's when we have the short direction of the sensor parallel to the axis of the telescope. Now, if we continue to rotate that around, we'll have the bright spot on the short side, and that's when the long side of the sensor is parallel to the axis of the telescope. Now, what I'm going to do, because you saw there's a whole region where there's a significant blackout zone, and we'll take a closer look at this in a minute, I'm going to orient this thing so that the short side of the sensor is parallel to the axis of the telescope. And what I'm trying to do here is center the bright spot of the light along the mid-length of that long edge there. So here's a contour map of the light coming into this guide camera sensor. And in this case, the guide camera is oriented so that the short dimension of the guide camera sensor is parallel with the telescope. Now, there's a couple of things that I found surprising about this that I didn't realize was happening until I just did this recently. First of all, I didn't realize that the imaging sensor is seeing a bright spot and that the light is falling off fairly rapidly. What I expected to see is a more or less uniformly illuminated sensor. So I expected these contours to kind of follow the circle lines of the light coming in. I expect the light to be nominally equal in circular bands going around here. And in fact, I'm getting a hot spot, a bright spot about right here on the mirror. And sure enough, if we look at the same contours when the image is rotated, that's where this bright spot, is. So I don't know what's causing that. It could be that the mirror is not as flat as one would hope. I don't have a good explanation for that, but what this is showing you when you look at the orientations of the guide camera in these two cases, I think I'm getting more use of the sensor when I'm oriented in this direction with the short side parallel to the axis of the telescope. I recorded this video with a constant and uniform light source over the entire diameter of the corrector plate from my light panel, and yet I'm getting a very non-uniform light coming into the guide camera. And this was a little disappointing given that I bought the ASI-174, a pretty expensive guide camera, because I wanted this large sensor and to take advantage of this large sensor for finding guide stars with a high focal length system. I wouldn't, however, say that the ASI-174 is a bad pairing, because if you look at what an ASI-290 looks like, this is what you're looking at in terms of its field of view. We can still make use of guide stars that are around this periphery, mostly on these three sides here, that we wouldn't be able to make use of with the ASI-290. In order to use this setup in Stellarium, what you want to do in the Oculars tab is go to the Sensors tab and then enter in the information for your sensors. So for me, that's the ASI294MC. I've got the resolution in pixels in the X and Y directions. I've got the length of the sensor in millimeters and the height in millimeters. And then if you come down here and click on this tab here, it will open up the off-axis guider section so that you can enter in information and show the field of view of the off-axis guider. One of the things that seems to be a bit confusing with some people is this first entry up here. And if you hover over it, this is the tooltip that will pop up. It says that what you should enter into here is the distance from the center of the imaging sensor. So the center of the imaging sensor is at the center of this circle here. So we want to measure from here up to, it says, the bottom of the prism. That's not quite correct. You want to enter the distance from the center of the imaging sensor up to the bottom edge of the guide sensor if the guide sensor is smaller than, which it probably is, the prism, which in this case is 12.5 millimeters. So this is the number you want to put into that box. You don't have a point to grab onto with calipers in here. So what you can do is measure the inner diameter of this piece of the off-axis guider. I got 73 millimeters. Then you can measure from the bottom of that same circle up to the bottom of the prism. I get about 47 millimeters. And then you just do some simple math. Take the 47, subtract off 1/2 of the 73, so that gets you to this distance right here, but that's not the distance I want since my guide sensor is smaller than this. So now I want to go to the center line of the prism, so that's add on 12.5 divided by 2, and then come back down, subtract off the guide sensor width divided by 2, and that leaves me with 13.2 millimeters. And so that's what I'm typing into this box here. Now, the other two boxes are just the size of the imaging sensor. Now, again, you're going to enter in the smaller of the number, whether it's the width of the prism or the width of the sensor, or the height of the prism or the height of the sensor. So in my case, the sensor is smaller than this prism with the ASI-174. So I'm putting in ASI-174 numbers of 7.1 in the box that's behind this tooltip and 11.3 in this box here. Another thing that I do with Stellarium is I set the stars that it shows to only have magnitudes from about 11.5 magnitude and brighter. I have found that I can guide on those stars with adequate signal to noise ratio. However, while I can see stars that are more dim than that, it is difficult for me to get good guiding with them because I don't have a good signal to noise ratio for those stars. Now, when I can go into Stellarium with the Oculars tab activated and the numbers that I just typed in, this is my imaging sensor here. And maybe if I'm lucky, I can just fit the Leo triplet in if I aim properly. And with the guide camera shown here, as I've oriented it, the short side of the sensor parallel to the axis of the telescope, these are the stars that I have. at least over here. You can see there's a couple of stars, although based on what we're seeing with that contour map, this guy may be a lost cause. This will be perfect because it's pretty close to that bright spot. But the thing is, these are the stars on one side of the meridian that I have. If I go over to the other side of the meridian, based on what I'm seeing here in Stellarium, I don't see any stars with a magnitude of 11.5 or brighter over here. So that could be a bit of a challenge for this target. When you look at the M81 and M82 pair of galaxies, there's quite a few stars in this outer annular region. I have a pretty good setup here for getting stars on this side of the meridian and a nice star here 180 degrees away on the other side of the meridian. So this won't be much of a challenge. So I hope to improve my RGB imaging of galaxies this galaxy season by having a dedicated one-shot color camera, the ASI294MC, mounted on my SCT, which means I will share my ASI294 monochrome between the Red Cat and the GT81, and then confine my ASI 1600 to the 8102s. So I'm sort of slowly drifting towards the direction of having dedicated imaging systems. I'll use a filter drawer here. I don't need a full populated filter wheel, so just having a filter drawer with one RGB filter that provides some light pollution protection and one dual band filter that provides the narrowband data from the oxygen 3 line and the S2 and HA lines is all that I'll need with a one-shot color camera. So I'm hoping I'll still be able to shoot some nebula or pull out some hydrogen alpha in the galaxies. And I'm going to try using the focal reducer to hopefully mitigate some of the concerns I do have about using a one-shot color camera with a dual or tri-band filters. I'm going to be feeding filtered light into the focusing algorithm and into the plate solving algorithm. And so ideally, I'd like to have a little brighter images to start with and more stars to work with. So the focal reducer will give me a wider field of view and more light and more stars. And hopefully that will reduce some of the challenges that I will have doing autofocus and doing plate solving. Measuring back focus has been a struggle for me in this telescope because Celestron does not effectively document where to measure the back focus from, or even what the back focus is for a given scope. You've got to go searching for it. But it certainly seems like with my telescope, the C925, the non-edge C925, I need to be measuring 139 millimeters back from the back end of the threads on the SCT, or 105 millimeters from the back end of the threads on the focal reducer. The ASI294 has a high conversion gain that kicks in at about a gain of 120, so I'll probably shoot all of my filters at 120 to 122, somewhere in there, just to make sure I've engaged that high conversion gain. Now, having higher gain with broadband filters is a problem because you really got to cut back on your exposure time, otherwise you wash everything out. But using high gain with a tri-band RGB filter or a light pollution filter like the L Pro, that may work out okay, and it may help me to use longer exposure times, the high conversion gain value of 120. I'll be talking more about the L Pro versus the Antlia tri-band. The tri-band cuts out more light than the L Pro, so that's going to be something interesting to study with some test images. That's the theory. Now, let's just get outside and see what really happens. Okay, guys, well, that's all I have for now. More troubles to follow. I hope I didn't just screw this thing up. See ya.